So today we're talking about some stuff out of Unit 5-6, equations of lines in the plane and space. And first off, we want to start talking about linear combinations of vectors. Now we've looked at linear combinations of vectors a little bit in Unit 1-2 and in Unit 3-4. So some of this stuff is going to be a bit of a review. But what we want to do here is we want to bring a lot of these concepts together, and we want to sort of nail down a little bit of terminology to make things that you're going to encounter in the textbook a little bit more clear. First off, what is a linear combination of vectors? Well, we've got the definition up here. It's formed simply by adding scalar multiples of vectors. So if I've got two vectors, u and v, and I want to form a linear combination of these, I can do something like -4 times u, add that to, I don't know, 5.7 times v. Okay? This would be a linear combination of these two, of u and v. So is a linear combination of vectors u and v. Now what makes this linear here? Well, because all I'm doing is I'm doing scalar multiplication and I'm doing vector addition. I haven't multiplied either of these vectors u and v by another vector. So I haven't done the dot product or the cross product. I haven't squared any of these vectors or anything like that. I'm just doing these linear operations here. So in general, we can say that some vector x is a linear combination of two other vectors, u and v, if we can write x as some scalar a times u plus some other scalar b times v, okay, where a and b are both scalars. Okay. So linear combination, we can write it as a sum of the scalar multiples of these two other vectors. Now this is another way of saying that x, u, and v are linearly dependent. Okay. And that's a term that the textbook is going to use a lot. Okay. So if we can take one of these vectors and make it, in this case x, as a linear combination of the others two, that means the three vectors that we're looking at are linearly dependent. Okay. Okay. So, and we've seen this before, linear combination, we're just sort of equating this with the idea of something being linearly independent. The next term that the textbook uses a fair bit is collinear and coplanar. Now, collinear, we've encountered a little bit before. Collinear just means that the two vectors are on the same line. So here I've got two vectors, x and v. These are clearly collinear because these two vectors are lying on the same line. Okay. Another way of saying that two vectors are collinear is to say that they are scalar multiples. Because I can take some scalar, multiply it by x, and I will get that vector v. Okay. So, i.e. scalar multiples, what we're saying here is that vector v is some scalar a times vector x, where this again is a scalar. Now, we've encountered this concept of scalar multiples before, and if two vectors are scalar multiples of each other, what did we know was true about the two vectors? One, two, I think it was. Well, if one vector was a scalar multiple of the other one, we knew that the two vectors were parallel. So let's just say the two vectors are parallel. Now, this might seem a little bit odd. I'm saying that they're collinear, which means they lie in the same line. I'm also saying that this means that they are parallel as well. And the reason that this is true is because these vectors aren't anchored to any specific spot in space. I can take this vector v, okay, and I can move it around like this, okay, and I can move x around like this. If I look at them here, clearly these two vectors are parallel, okay? But because I can take vector v, and it's still vector v if I move it here, put it up there like that, that means that if I were to put vector v, tip to tail in this case, the two vectors would be collinear. So saying that two vectors are parallel is another way of saying that I could move one vector onto the other one and the two would be collinear. So mathematically, these two concepts of being collinear and being parallel and being scalar multiples are all the same when we're dealing with two vectors here. Okay? So these terms they're not used interchangeably, but they sort of mathematically they mean almost the exact same thing. So collinear means they're in the same line. Next up, coplanar. If vectors are coplanar, that means that they lie in the same plane. And we're going to encounter this a lot when we get into three-dimensional vectors. So here I've got sort of two planes. I've got a purple plane and I've got a green plane, and I've put a couple of points in each one here. I can make some point-to-point vectors between the points in our plane here. So I could say if I go from m to n, I make the vector mn. If I go from O to P, I get the vector OP. And because both MN and OP, all the starting points and the ending points are both located in that purple plane there, these vectors, MN and OP, are coplanar. And of course, I could do the same thing for these other points that I've got. I could say that the vector QR and the vector SU are coplanar as well. Because they join points that are both lying in that the green plane there. Okay. Something like, however, MN and QR aren't necessarily coplanar. So MN and QR are not coplanar. Okay. So anytime you're dealing with two-dimensional vectors, all of our two-dimensional vectors lie in the xy plane, okay, that we've looked at so far. So all 2D vectors are coplanar. It's only once you start getting into three-dimensional vectors that you have to worry about whether or not two vectors lie in the same plane, whether or not they're coplanar. So if three vectors are coplanar, we can express one of these vectors as a linear combination of the other two. So we could say if we've got three vectors, x, u, v and u, again, if we can again write x equals a plus b times u, that means all three of these vectors are coplanar. Which again is just another way of saying that they are linearly dependent. So if three vectors are coplanar, they're linearly dependent. If three vectors are linearly dependent, then they must also be coplanar. Okay? And this is sometimes written as 0 equals x plus AV plus BU. That you can take all three of these vectors, add them together, and end up with 0. Okay? And I mean, to see why this works, you can imagine having these vectors here, x, v, and u. X, v, and u here all lie in the plane of the smartboard here. If these three vectors are coplanar, I should be able to take any two of these vectors, add them together, and get the third one. So I should be able to take u and v, add them up, and somehow place them tip to tail, and somehow to get x. Well, if I just place them tip to tail, I clearly don't have x. But what I'm allowed to do is I'm allowed to multiply each of these vectors by some scalar. So if I scale up my vector u here, make it a lot bigger, make my x a lot bigger here. Oh, that's too big, maybe. Okay. I should be able to, if I get just the right scalars here, yeah, I can take this now scaled up version of u, add it to v, and get my scaled up version of x. Okay? And if I fiddled around with that, I could do that for any of these vectors that I was able to draw, as long as they were all in the same plane. So what kind of questions are you likely to encounter where you've got to apply this knowledge? Here's a typical question. Okay? You're given three vectors, x, u, and v. Okay? X is 7, 4, 15, u is 4, 1, 16, and v is 5, 2, 9. And we'll put little vector symbols over top here. Okay? We are told that these things are coplanar. Okay? Oh. That's on. All right. So we're told that they're coplanar. Express x as a linear combination of u and v. Before we do that, show x, u, and v are coplanar. Okay. There are two ways of showing that three vectors are coplanar. One of them is to write one of them as a linear combination of u and v. We're going to end up doing that anyways. There's a shorter way of doing that, and that is to evaluate the triple scalar product of these three vectors. If I take the triple scalar product here, x cross u, and I dot it with v, okay, if this equals 0, okay, x cross u dot v equals 0, then they are coplanar. Now, why does this work? Well, think about this. If we assume that they're coplanar, that means x, u, and v all lie in the exact same plane. Okay? If I do the cross product between x and u, what that gives me is, well, what does that give me if I do a cross product of these two vectors here? What kind of a vector do I get out after doing the cross product? What do I know about it? Tasha? Yeah, it's going to be perpendicular to x and u. So it's going to be perpendicular to the plane that all of these lie in. Well, if I take the dot product of a vector that is perpendicular to the plane with a vector v which lies in the plane, and I should get 0 if this is perpendicular to the plane and this is in the plane. So this equals 0 if v is in the plane. Okay. So showing this just amounts to doing a cross product and then a dot product. So we can set this up. Let's do x cross u first. So if I do, let's see, where is this? So our triple product is going to be 7, 4, 15 crossed with 4, 1, 6. And then I'm going to do the dot product of that with 5, 2, 9. Okay. So let's do our cross product here. We can set this up over in the corner. We can say I, j, k. We've got 7, 4, 15, 4, 1, 6. I is 7, 4. Okay. And then we can work this out. So when I do this, I end up with 9, 18, negative 9, which then we're going to dot with 5, 2, 9, which works out to 9 times 5 is 45, plus 36 minus 81 gets us 0. Okay. So if it just asked us to show that these things were coplanar, that's the calculation we want to do, because that demonstrates it. Okay. Now, if we go back to the original question here, we're asked to express x as a linear combination of u and v. Let's take a look at how we would do that. If we want to put x as a linear combination of u and v, that means we're going to write x equals some scalar times u plus some other scalar times v. So we really just want to find these two scalars, a and b. Find a and b. Well, let's put in what our vectors are here. X was 7, 4, 15. U is 4, 1, 6. And V is 5, 2, 9. The key to solving this kind of question is we can treat our x, y, and our z components separately. So we'll separate our x, y, and z components. So if we look just at our x components here, the relationship we're going to have is that 7 equals a times 4, or 4a, plus b times 5, or 5b. If we look at our, that was our x components. If we look at our y components, what we're going to have is 4 equals 1 times a, or just a, plus b times 2, or 2b. And if we look at our z components here, we're going to have 15 equals a times 6 is 6a, plus b times 9 plus 9b. So where these were our x's, our y's, and of course these down here are our z components. So where can we go from here if we want to figure out what a and b are? What do we have here? Yeah. Yeah. What we've got here is a linear system of 3 equations with 2 unknowns, a and b. And you guys have been solving linear systems since you were in grade 10. There are 2 methods you guys learned, substitution and elimination. So in this case, we could probably do this using substitution. We can pick 2 of these and then start solving. So we can take this guy. Let's isolate this for a. So a is going to equal 4 minus 2b. And then let's take this and sub it into our x equation there. And we'll end up with, let's come down here, 7 equals 4 times 4 minus 2b plus 5b. And now let's solve this thing for b. 7 equals 16 minus 8b plus 5b. We'll bring the 16 over to this side and get negative 9. Negative 8b plus 5b is negative 3b. So b is going to equal 3. Which means a is going to be 4 minus 2 times 3, which is negative 2. Now, if we were worried that we had done this incorrectly, there's a way of checking our answer. We have this third equation for z sitting around that we haven't used yet. So we can plug our values of a and b into our z equation and see if this whole thing works. So kind of like the old left side, right side check. We've got 15 on the left side. On the right side, we've got 6 times negative 2 plus 9 times 3 is going to give us negative 12 plus 18. Sorry, plus 27. Which, yeah, sure enough, gives us 15. So let's say we'll check this in our z equation. So we can sum all of this up by saying that x is going to equal, let's see, we said it was a times u, so negative 2 times u plus 3 times b. Okay. And there we are. There's x as a linear combination of u and v. Make sense? All right. So this is basically grade 10 math with some strange terminology thrown in. Okay? The idea of, they'll phrase it in terms of, are these vectors coplanar or are they linearly independent? But the calculations or the math that you have to do is stuff that you did way back there in grade 10. And in fact, everything we do in this vectors portion of the course, you learned in grade 10. Okay? It's just applying it to new situations. Okay. All right, let's take a look at one more example here, and then I think we're done. We've got 3 vectors, u, v, and x. We're told their magnitudes are, u has a magnitude of 6, v has a magnitude of 10, and u has a magnitude of 30. we're told something about the angles that these things make. Each of them makes angles of, well, they make angles of 0 degrees, 60 degrees, and 210 degrees with the positive x-axis respectively. We want to express x as a linear combination of u and v. It probably should be x. Let's see. That would make a lot more sense, wouldn't it? Yeah, let's change that to x. Okay, so we fixed that. Now, x has a magnitude of 30 degrees. And we want to express x as a linear combination of u and v. The textbook does a number of examples, questions like this. And what they do is they do these questions geometrically. They draw out the vectors, they very carefully rearrange them so that they form a triangle, and then they use sine law and cosine law to figure out what the coefficients are. I think that's the hard way of doing it, okay? Because we spent all of the last unit learning how to use Cartesian or algebraic vectors. And we found that they were a lot more convenient to use than geometric vectors. So I don't know why we would throw that all away and rush back to doing these things geometrically. So what we're going to do is we are going to take each of our vectors, turn them into Cartesian vectors or algebraic vectors, and then solve the question that way. So let's start by figuring out sort of how our vectors are related here. So we'll do a picture of what our vectors look like, just so we can get a sense of what we're going to do here. So vector u makes an angle of 0 degrees with the positive x-axis. So u is going to be down here like this. This is u. The magnitude of u is 6, and it's right there on our x-axis. V has a magnitude of 10, and it makes an angle of 60 degrees. So we can draw V kind of up here like this. The magnitude of V is 10. We've got an angle in here of 60 degrees. Our third vector is x. It has a magnitude of 30, so it's considerably bigger than the other two. And it makes an angle of 210 degrees with the positive x-axis. So we'll just draw x down here like this. And this angle all the way around here is 210 degrees. Those are our three vectors. So let's turn these things into algebraic vectors. So, as algebraic vectors. U is the easiest one. Okay? It only points in the positive x direction, so it only has an x component. So that x component has to be 6, and the y component has to be 0. V and x are going to be a little bit trickier. But if we think back to when we talked about, way back to how we talked about how you went from geometric to algebraic, we said that you had to imagine a little right angle triangle here, and using the sine or the cosine of this angle that we're given. So V, the x component of V is going to be the magnitude of V times the cosine of that angle, 60 degrees. And the y component is going to be 10 sine 60 degrees. So we can work out what that is. It's just 5, 8.66, okay, to round it off to 2 decimal places. We can do the same thing for vector x here. Now, V was pretty easy because it's located in quadrant quadrant 1 there. We got to remember the cast rule here. Okay. Well, actually, we don't have to worry about the cast rule. We have to think about whether the ordered pair, the x and the y value, are going to be positive or negative. But because our angles are measured here from, like if we just visualize, okay, this ordered pair here that's going to represent the tip of vector x here, what do we know about the two components? What are the signs of the two components? Yeah, they're both going to have to be negatives. This is going to be negative something and negative something. Okay. So we can either work that out, or in this case, because we're given this 210 as the angle from the positive x-axis, or the angle is given in standard position, if we use that angle, the sine and the cosine, because of the cast rule, automatically picks out the sign that those two components should have. So if we just say that our x component of vector x is going to be 30 cos 210, and our y component is going to be 30 sine 210, because in quadrant 3, both sine and cos are negative, that automatically makes those two components have negative signs on them. So we punch this in, we get negative 25.98 and negative 15. Now the question is exactly the same as the last one we did. We want to express x as a linear combination of u and v. So we can write x equals au plus bv. We can put in our vectors that we've just calculated here. So we figured out that x was negative 25.98, negative 15, equals a times u, we figured out was 60, b times vector v here, which was 5 times 8.66. And then we do the same thing we did last time. We separate out our x and our y components into separate equations. So from our x components, we get negative 25.98 equals 6a plus 5b. From our y components, we get negative 15 equals, well, a times 0 just gives us 0. So we get 8.66 times b. This one's even easier to solve. We can solve that y equation directly. Okay. So b is going to be negative 15 divided by 8.66, which is just going to give us negative 1.73. We can sub that back into our x equation. So 25.98 equals 6a plus 5 times negative 1.73. And so we're just subbing this into a, sub into the x equation. We rearrange all of this stuff, and we get a equals negative 2.89. So we can finish the question off by actually writing x is a linear combination of u and v using these two scalars that we just found. So x is going to equal negative 2.89u minus 1.73 times v. And there's our final answer with those u and those v components in there. Okay. So the method you use is up to you. You can do it geometrically, following the example that the textbook does. I just think this is a lot easier, converting them into Cartesian components and then solving the system of equations. Okay. And I think that's where we're going to stop today.